All right, let's do another example of implicit differentiation. Okay, it takes a while to get used to, but let's try another one. The more that you do, the better that you will get at doing it. So let's find dy dx for this weird looking function. Now, that's certainly not given explicitly in terms of x. We've got y's scattered all over the place. We don't even want to bother with trying to solve for y. So let's find the derivative implicitly. So I'll start off by saying, all right, dy dx is what we want. So that means we're going to find the derivative with respect to x on both sides. And just as I write this down, I'm going to rewrite those radicals as the fractional exponents just to get them ready for the derivative. Okay, so the derivative with respect to x on both sides. Okay. Here we go. So the derivative on each side. So I'm just going to kind of go through, and since we've got a sum in here, we can do the derivative of the sum separately. So first of all, the derivative of x is 1. Okay, remember, we're taking the derivative with respect to x. But now's where it gets a little bit more weird. We have the derivative of a product. Okay, so we do need to do a product rule here. Okay, so here we go. First, I'm going to use extra parentheses to really emphasize where each piece is coming from. So that's first times the derivative of the second. Okay, so the derivative of y to the 1/2. There's a chain rule here because we're assuming that y is a function of x. So it's going to be the power rule on the outside of it, 1/2 y, reduce the power by 1, and then times dy dx. Okay, there's always that chain rule popping out from the y. Okay, so that's first times the derivative of the second plus the second, so just the y to the 1/2, times the derivative of the first. So the derivative of x to the 1/2, just regular power rule, 1/2 x to the negative 1/2. Okay, we don't have to have any other chain rule popping out because this is the derivative with respect to x. Okay? So that's first times derivative of the second plus the second times derivative of the first. Okay, equals. On the right-hand side, okay, so that's going to be a chain rule. Y is a function of x. So just do the power rule on it, 2y to the first power, and then times dy dx. Again, every time you take the derivative of the y, just take the derivative how you normally would, but that chain rule has a dy dx pop out. Okay, so that's the derivative process. Now what we need to do is we need to get dy dx by itself. Okay, so I'm seeing that it's located in 2 different places. So we need to do that same technique from example 1, where you want to get everything with the dy dx in it on one side of the equation, and anything with a dy dx not in it on the other side of the equation. Okay, so let's clean this up slightly before we get started with that, because there's a lot of different ways that we can clean this up. Okay, so let's go, how about 1 plus, okay, so what's going on here? I see x to the 1/2, and I also see this 1/2 y to the negative 1/2, so I'm going to put the 2 from the 1/2 down there, and the y to a positive 1/2 down there. Okay, just a little bit of cleaning up, and then we still have that this is times dy dx. Okay, then we have plus, and then over here, similarly, I see this y to the 1/2 that I can leave on top. And then with this 1/2, a 2 can be down there, and then x to the positive 1/2 down there. Okay, and then over here, nothing to do, 2y dy dx. Okay, just cleaning it up a little bit. So still, we want to get dy dx by itself. But before we do that, there's so many different ways that we can proceed now with some algebra to just clean all of this up. And rather than having to deal with dividing by a huge mega fraction at the end, I think I'd rather just clear the fractions right now. So I'm just going to make a note. We're going to multiply. I just want to clear fractions right now. Okay, multiply both sides by, okay, the common denominator of the fractions. And I'm not talking about like the dy dx things. I'm talking about the other parts, the 2y to the 1/2 and the 2x to the 1/2. Okay, so the common denominator with both of those, they both have a 2. And I need a x to the 1/2 and I need a y to the 1/2. Okay, so I'm going to clear fractions by doing that. Okay, so let's see, how much space do I have? Okay, I got a lot of space. I'll write that out. So we're going to go 2x to the 1/2, y to the 1/2 times all of this. Okay, and both sides of the equation. Okay, this is going to clear all of the fractions. Our final answer is probably still going to be pretty crazy looking, but this is going to avoid some problems dealing with bigger fractions later. All right, so let's be a little bit careful. We have to distribute this into everything on this side. So don't forget there's that 1 there. That 1 just takes it all. So 2x to the 1/2, y to the 1/2, just from the 1. Okay, then when we distribute onto this part, we'll have plus. Okay, so be a little careful. The 2's will cancel, and the y to the 1/2 will cancel. So all that is left is x to the 1/2 times that other x to the 1/2. And that's really nice because the 1/2 plus 1/2 will add up to x to the power of 1. Okay, take a minute, look at that, make sure you agree with that. The 2's cancel, the y to the 1/2's cancel, and the x to the 1/2 times x to the 1/2 is x to the 1. Okay, all of this is multiplication here, so that's still attached to a dy dx. Okay, and then similarly, when we distribute all the way over here, we'll have plus. Okay, starting over, again, it's going to be a similar process. The 2's will cancel, the x to the 1/2 will cancel, and we'll be left with y to the 1/2 times y to the 1/2, which is just y. Okay, so that simplified quite a bit there. On the right-hand side, just multiplying straight through here, not too much to do besides 2 times 2 there is a 4. Then there's still x to the 1/2. And then be a little careful, we have y to the 1/2 times y. Okay, remember that the powers add up. So there's like a little 1 right there. So if you want to think about the y to the 1, it's the same as like y to the 2/2 power. So those powers add up. It's going to be y to the 3/2 power. Okay, and then there's still this dy dx there. All right. So a little bit messy there, but that'll probably keep our answer a little bit more under control compared to what we might have needed to do later on. Okay, now what we want to do is that same process. We want to get all of the dy dx terms on one side and anything that does not have a dy dx in it on the other side. And so for me, I always like to get the dy dx to the left-hand side. I don't know why, but that's just what I usually like to do. So let's get rid of this term by subtracting that on both sides. And I also need to get rid of that y. So we're also subtracting that y from both sides. Okay, so that's gone and that's gone. And then I need to get this dy dx mess thing moved over to the left-hand side to join the other dy dx thing. So I'm going to go minus 4x to the 1/2 y to the 3/2 dy dx. Okay, so I'm doing a lot of steps at once here, but hopefully you can see the theme there. We're trying to get anything with a dy dx in it on one side and anything without a dy dx in it on the other side. Okay, so on the left-hand side, I remove those two pieces. So now what's left is that x dy dx. And then there's this minus 4 x to the 1/2 y to the 3/2 dy dx. And then over here on the right-hand side, we canceled out that big dy dx term, and then we subtracted these two other terms. So we've got just minus 2x to the 1/2 y to the 1/2 and minus y. Okay, almost there. We've got dy dx as a GCF on the left-hand side, so let's factor that out. So factoring out dy dx, we would have x minus 4x to the 1/2 y to the 3/2. Okay, removing the dy dx from both terms. Okay, and then almost done. Divide both sides by that mess. Okay, so full canceling here. And we're left with our answer, dy dx equals. And so there's that. I'll just rewrite it again. And maybe to write our final answer, I'll rewrite it with, instead of fractional exponents, let's rewrite them wherever possible as, because we were given radicals in the first place. So maybe it's a good idea to rewrite the final answer in terms of radicals instead. Okay. So yeah, let me think just a second here, because we've got that stuff, the 4, okay, and then this y to the 3/2. I was just thinking about this. I can't really get that in terms of a radical. So, oh, I don't know, it kind of doesn't matter how we write our final answer. I was thinking maybe I want to switch it back to radicals. Maybe I'll go ahead and just write it as minus 2 root x root y. And then there's that minus y. And then in the denominator, we have x minus 4 root x. And then that's y to the 3/2 power. So we could write that if we wanted to get, okay, yeah, I'm going to get a little bit fancy here just for fun. Y to the 3/2, if we want to write everything in terms of radicals, that's the same as y times y to the 1/2. Would you agree? That's kind of just some scratch work. Okay, just so that we can rewrite everything in terms of radicals. Not really necessary. I mean, especially if you're entering your answer, I wouldn't be too picky about taking off points, or if it's like some kind of a enter the answer onto the computer, it should accept any algebraically equivalent statement. Okay, so anyways, I'm just doing this. I'm going to go x minus, and then there was this 4. And then I'm rewriting that y to the 3/2 like this. So I'm going to have a single y out there. Okay, that's this y. And then there's this radical x and the leftover radical y. Okay, not really any real reason to do that, but that would be one option. Okay, so I'll go ahead and put a box around that, just for a nice, clean looking answer. Okay, and I'm noticing another thing, not really necessary, but if you prefer, again, a lot of times it's just algebra and your preference. I could factor out a negative from the numerator so that those are both plus. And then if I factor a negative out of the denominator, those would just switch the order. And I really want to show this, so I am going to actually show the work there. If we factored out, so I'm just going to show you some extra. This is not technically necessary, but it's good to be able to notice lots of different options for how to simplify your work or rearrange the work. Okay, so I'm noticing if I factor a negative out of the top, then it switches those to both plus. And if I factor a negative out of the bottom, it's going to turn this minus 4y stuff into a positive. So I'll write that in the front. And then that positive x would now become a negative x if we factored a negative out. Okay, and then the point of doing that is then you have negative over negative cancels, and we have an equivalent answer. And it kind of depends if, because like I said earlier, I like to move everything with the dy dx in it to the left-hand side. But if somebody else moved everything with the dy dx in it to the right-hand side, I'm pretty sure they would have gotten this version of the answer with those negatives factored out. So 2 different versions of the answer that's the same. Just wanted to show you some options. Okay, and then this one is technically a little bit cleaner because we don't have extra negative symbols in the numerator there. Okay, so this is just another equivalent answer. Both would be totally acceptable, but just wanted to show you that it's a common technique to just be able to rearrange it slightly. All right, so like I said, dy dx, we're able to find the derivative with respect to x in kind of this loophole technique, and we still have x's and y's all scattered around over there, but if we're going to plug in different values for x and y to start thinking about rates of change and tangent lines, then we have dy dx. And so in example 3, we're going to try to think about the equation of a tangent line to some crazy looking graph right there. Okay, so stick around for that.